All right, let's get right into it. Back in 2012, something happened that completely changed the game for artificial intelligence. A piece of software did something that honestly sounded like science fiction. It learned to see the world with almost unbelievable accuracy. This is the story of AlexNet.
For the longest time, this was one of the biggest challenges in computing. Teaching a machine to tell the difference between a cat and a car or a flower and a bicycle, it was just incredibly hard. So how did we get from that to the powerful AI we have all around us today? Well, the answer really hinges on a single groundbreaking moment.
To really appreciate just how revolutionary AlexNet was, we first have to talk about the competition that set the stage for this huge leap forward.
This was the ImageNet challenge, basically the Olympics for computer vision. It was this intense test where different AI models would compete to correctly identify objects in millions of different images. And for years, progress was, well, it was slow. The best models were only getting better by tiny little fractions of a percent each year. It really felt like the whole field was hitting a wall.
But in 2012, a new contender stepped into the ring. And it wasn't just a little bit better than what came before. No, this was a massive quantum leap forward.
And this really shows you the scale of the win. AlexNet didn't just edge out the competition, it completely blew it away. It slashed the error rate by such a huge amount that it forced the entire research community to just stop and pay attention. The era of slow, tiny improvements was over. The deep learning revolution had officially begun.
So who were the brains behind this whole operation? It was a small team from the University of Toronto, Alex Krzyzewski, who the network is named after, Ilya Sutskever, and their supervisor, Geoffrey Hinton, a guy who's often called the godfather of deep learning. Their work showed that a deep neural network could do what many people thought was impossible.
But here's the thing. The ideas behind deep neural networks had actually been around for a while. So why then? What was the secret sauce that made it all work in 2012? Well, the answer wasn't just in the software. It was in the hardware.
The big problem, the major roadblock for years, was just a lack of raw computing power. Training these huge brain-like networks takes an incredible amount of processing horsepower. For a long time, your standard computer processors, or CPUs, just couldn't handle it. They were way too slow. Trying to train something like AlexNet would have taken forever.
And this chart, this shows the solution perfectly. The team had a brilliant idea. They used graphics processing units, or GPUs. The chips originally designed for making video games look awesome. Turns out they were also perfect for the kind of math deep learning needs. And just look at the difference here. The jump in processing speed from CPUs to GPUs isn't just a small step. It's a giant leap that finally unlocked the true potential of these networks.
Okay, so we know it was a huge deal, and we know what piece of hardware made it all possible. But how did it actually work? Let's pop the hood and take a look at the anatomy of this digital brain. Now, at first glance, this might look really complicated, right? But don't worry. The easiest way to think about it is like a factory assembly line, but for images. A picture goes in one end, it passes through a bunch of different stations, and a final decision about what's in the picture comes out the other end.
This entire assembly line is built from just 8 main layers. That's it. Think of them as 8 distinct stages, and each one has a very specific job to do, all working together to turn a bunch of pixels into a real understanding of what the image is showing.
And those 8 layers can be broken down into 2 main types. You've got 5 of what are called convolutional layers, which do the first pass of visual processing, and then you have 3 fully connected layers, and that's where the final thinking and decision-making happens. So what the heck is a convolutional layer? Well, imagine you have thousands of tiny little magnifying glasses, and each one is trained to look for one specific thing. One looks for straight lines, another looks for sharp corners, maybe another looks for the texture of fur. They scan all over the image and basically shout, "Hey, I found one," whenever they see their special feature. So if we look back at our assembly line diagram, you can see these 5 convolutional layers marked with a C. The first ones in the line learn really simple things, like edges and colors. But as the image moves down the line, the later layers start combining those simple things to find more complex shapes, like an eye, or a wheel, or a leaf.
Now, after some of that feature detecting, things can get a little messy. So AlexNet has this really clever cleanup step called a max pooling layer. Its job is basically to keep only the most important information and kind of toss out the rest. It's like it says, okay, we definitely saw an edge somewhere in this little area, that's all that matters, which makes the whole network run faster and more efficiently.
And back on our map, these are the S layers, which stands for subsampling. See how they pop up right after the convolutional layers? They're there to condense all that information before passing it to the next stage.
Okay, so finally, after all the features have been found and simplified, all that information arrives at the fully connected layers. This is like the network's command center. It looks at all the signals it's getting, the presence of edges, corners, textures, complex shapes, and it weighs all of that evidence to make a final, educated guess.
These are those last 3 layers, labeled with an F. This is where it all comes together. This is the part that finally says, okay, based on the evidence of whiskers and pointy ears and a furry texture, I'm 95% sure this is a picture of a cat. And that, right there, is how a computer learns to see.
AlexNet's incredible victory in 2012 wasn't an endpoint. It was really the starting pistol for a race that is absolutely still going on today. Its impact is still being felt across the entire field of AI.
So what was its lasting impact when you boil it all down? Well, first, it proved that these deep convolutional neural networks were, without a doubt, the future of computer vision. It also made using powerful GPUs a mainstream practice. And its architecture introduced some really clever new tricks that pretty much became standard tools for AI researchers everywhere.
But the most important takeaway is this. Its success triggered this massive wave of investment and research into deep learning that led directly to the AI technology we see all around us now, from self-driving cars to medical scanners and all the generative AI today.
It's a really powerful legacy. AlexNet literally opened the door for machines to perceive and understand our visual world. And it really makes you wonder, what's next? What sense are we going to give them next? Hearing? Touch? Or maybe even a sense that we humans don't have at all? The revolution is definitely far from over.